Okay, guys, so we're on to the second example problem that you're going to see today. Notice this is from the 2018 exam. The one that you looked at also today was from 2019. So these are the most recent examples we have, and they're also examples that cover a lot of ground. They cover a lot of sections. In fact, I'm going to pencil in next to each of these which sections of the book and which sections of your notes you would find these in. So these are great candidates for kind of a type of question. I'm thinking more like the 15-minute question, right? We've done slope fields and separable differential equations. We've done particle motion. We've done second fundamental theorem. We have done, at this point now, rate in, rate out problems. And so let's take a look at this. Okay, so here we're not even given a function at the beginning. We're given a table, right? So this is a type of question where they might ask us about a table. Well, let's look at part A. Use the data in the table to estimate the derivative, right? The derivative is the instantaneous rate of change, but we don't have a function we can actually take the derivative of. So if I wanted to see h prime of 6, h prime of 6 would, the best I could do to estimate that is to find the average rate of change between these two numbers, the one on either side of 6, closest to it. Remember that this x is kind of the input, so the years are the input. Here, the meters are the output, or y. So if you're doing average rate of change, which is just slope, right? Make sure that you do 11 minus 6 over 7 minus 5. You don't want to do it the other. Now, get your units right. I'll have you look at the solution video for that, but make sure y is going on top. I think if I recall earlier in the year, most of you guys got this right, but the guys that struggled mixed up their slope there. They put the x's on top by mistake. We look at part B. Explain why there must be at least one time such that the derivative equals 2. This comes from section 3.2 in our book, and that was about the mean value theorem. The mean value theorem said that if a function is continuous and differentiable over a given interval, closed interval, then there must be at least one moment, at least one time where the average rate of change equals the instantaneous rate of change. So if I'm trying to figure out where the instantaneous rate of change is, then that means I need to come up here and I need to find, is there any place where the average rate of change would equal 2? And again, I'm going to have you watch the solution video, but if you watch that, you'll see over this interval here, the average rate of change is 2, which means at some point there would have to be a place where the instantaneous rate of change also equaled 2. For part C, look at part C, trapezoidal sum, right? So the trapezoidal rule is involved. And in addition to that, it's not just trapezoidal rule, but it's the average height, right? So you got to use the trapezoidal rule to find it. This is kind of like saying 1 over b minus a times integral from a to b of f of x. But because we don't have a function, that gets replaced with the trapezoid rule. So this part, guys, comes, I believe the trapezoidal rule was in section 4.3. It might have been 4.2. And the average rate of change, this function that I'm circling now, that was in section 4.4 and was called average value. Okay, on to part D. The height of the tree can be modeled by this function, where x is the diameter of the base of the tree. When the tree is 50 meters tall, the diameter is increasing at a rate, right? So I start to see that increasing at a rate. They're talking about diameter. I'm starting to think to myself, this might be a related rates question, which it is. And so this is a related rates question, which I believe was section 2.6. According to this model, what is the rate of change of the height? So that would be dh dt. With respect to time in meters per year when the tree is 50 meters tall. So what we basically have to do is we have to take the derivative of that. Well, the derivative of g with respect to time is going to equal, well, I got to take the derivative of that, so what's that going to use? That's going to use the quotient rule. So I got low d high, which is also going to say, when I'm doing the derivative now, it's going to have dx dt minus high d low, which would just be dx dt, all over low squared. Right? So taking the derivative here is going to require me to use the quotient rule and all kinds of other stuff. So pay attention to solution video. I think the quotient rule came from section 2.3. So look at all the stuff we have here. Section 2.3, 2.6, 4.3, 4.4. Over here, this was section 3.2. That covers almost half the book. This came from the very beginning of chapter 2. I think it was 2.2 for that one. So, I mean, look at how much of the book this one question covers. That's the kind of thing that we need to be prepared for. Once you've watched all these videos, just go to the AP Classroom, sign in as you did earlier in the year when we did some work on there. There are 2 free response questions that you will need to answer on that website. So I would do it on my iPad if I were you, and get that practice in, especially for those of you who are taking the exam, because that's how you're going to take the exam. You're going to have to do it in kind of a box like that, like it is on the website. So we're going to start practicing not just the problems, but the way in which we're going to have to solve this AP test. Hope that helps, guys. Have a great day.